Today we'll look at work in the context of our thermodynamic system here, which consists of ideal gas molecules, and this work is due to the movement of the piston, and we assume the interaction between the piston and the wall is frictionless. Now suppose the gas starts from some state A and moves to state B, and we'll look at a pressure volume diagram to observe the changes in this system. So by moving from state A to state B, the volume of the gas is going to increase from VA to VB. So basically the gas expands, but the pressure here remains constant. So a situation where this occurs is if this piston is moved upwards by some distance delta y. So therefore the volume of gas increases, but this would cause a drop in the pressure, wouldn't it? So therefore heat must be added via this heat reservoir to keep the pressure constant. So remember that the pressure is due to the gas molecules bumping on the walls of the container. So if we look at the cross-sectional area of this piston, then the gas molecules bumping on this area are going to cause a pressure. And remember that work is simply equal to the force on that piston. So that's the net force multiplied by the displacement. And force is simply the pressure due to the gas molecules acting on that piston multiplied by that cross-sectional area in blue multiplied by delta y. And the cross-sectional area by delta y is the change in volume. So therefore the work is equal to the pressure by the change in volume of the gas. And because the gas expanded, we're going to take this work as negative. So effectively, in this case, the gas does work on its surroundings when the volume expands. So in this case, because the change in delta y is positive, then delta V is also positive, which is a change in volume. And therefore the work done is by the gas on the surroundings. But if we instead started from this volume of gas, so this supposedly is VB, and then we compress the gas to get to a smaller volume VA, so therefore delta Y would be negative, the change in volume would be negative, and negative of negative is positive. So work is positive when the surroundings do work on the gas. So because the volume is compressed, these molecules are going to bump on the walls more often, and therefore the energy of the molecules is going to increase. So we can observe that the work done is equal to the area under the pressure volume diagram. But what if instead our pressure is not constant? So we may have the gas going from state A to some state C, and then back to state B. So from A to C, the work done is 0. Because there's no change in volume, so therefore for the pressure to decrease as we go from state A to state C, then heat must have been taken out of the system by this reservoir. And going from state C to state B, we have the work done is equal to minus the area under this curve. And this could be proven using calculus, but we're not using calculus in this introductory course on thermodynamics. So calculating this area geometrically, what we have is the area of a trapezium is the length of the edges, so pressure at C, plus the pressure at B, which is the length of this edge, onto multiplied by the height of the trapezium. So that would be VB minus VA. So in this case, the work done is by the gas on the surroundings, which is going to be negative, isn't it? Because the gas expanded from state C to state B, then this change in volume is positive, and the gas did work on the surroundings. But how did this increase in pressure occur? Well, in this case, heat must have been added from the reservoir to cause that change in pressure. So really think about what causes these changes in the state of an ideal gas. And I'll see you in the next video.